Okay, so here's one of the big problems that a lot of people have when starting out with Nodal. And the problem is trying to understand and know what connects to what, or what things you can plug into what other connections and so on. Of course, normally in Lightwave we don't have this problem. For instance, the bone weight map I can only essentially connect a weight map to this input, because that's all that this drop down gives me options for. When I'm adjusting the rest length, all I can do is enter or type in a number here. I can't connect anything else to that input, for instance. But for the node editor, that's somewhat different, because you can do an awful lot of cross connection. Now, taken verbatim as it appears, it does seem reasonably simple, because of course things are color coded. So of course, you can plug a red to a red and a green to a green and a blue to a blue. That's pretty obvious. But what you do invariably see when you see some of the nodal networks that people come up with is they wind up cross-connecting things, like a blue into a red, or green into red, and so on, or a blue into a green, and it somehow seems to work, and red into green, and there you go. And of course this begs the question, what is happening, how does it work, what on earth is the node editor doing to convert this to the other, and it doesn't seem to make much sense. So, first of all, let's make sure that we've got a good clear understanding or a good clear knowledge of the different data types that are available, the different connection types that are available in the node editor. First of all, we have the red type, or color. Red connections are for colors or shaders. Then you've got the pink, or purple. If you read the manual it says purple, but on pretty much every screen I've got or had it looks pink to me. But anyway, pink, purple, call it whichever. This is an integer. An integer is basically just a number, but it is always a whole number. You can't have fractional numbers. So, 23, 72, 271, right up to millions, whatever. But an integer is always, always, always a whole number, positive or negative. Scalar. A scalar is also a number, but of course it can have decimals. It can be a fractional. A vector is basically a collection of three scalars, and it can represent either position, rotation, or a direction as well. And we'll talk more about vectors later on. To just give you a quick idea, you see here I have a ball in layout, and it has coordinates for its x, y, z position there. And as I change and move it around, those coordinates change, and of course as I rotate it, the coordinates change for its rotation. This is its vector, and of course you've got that for position, rotation, scale, of course, also. These are vectors. But when I say direction, you could, for instance, take a point somewhere in space and draw a line from that point to some other point in space, or possibly to the center of an object, whatever, and that would be a vector, a direction from one place to another. And of course, the beginning of that place would be a vector, a position, the end of that place would be a vector, a position, and the direction between them would be a vector. But as I say, we'll talk more about that after. Yellow are functions. Basically, they are for modifying or modulating other inputs or entire nodes. What you will find with functions is that this is one of the types of connections that never gets cross-connected. You only see functions connected to functions. You can wind up plugging them into other stuff, but it tends to work out very, very badly most of the time and has often unpredictable results. And materials, which are light blue, which are of course full material nodes. They only connect to material inputs. You try and connect them to other things, see, you just get completely incompatible connection types. This is the one kind of connection that you can only ever connect to its like. Material to material is it. Now, what you will also find is that sometimes cross connections are possible and sometimes they are not. For instance, if I take a scalar here, okay, and I try and plug it into the bump input here, we're of course in the surface node thing here, You see it just plain doesn't work. Plug it into bump, doesn't work. Plug it into normal, doesn't work. So one might assume from this that, you can't plug a scalar into a vector. But that's not actually true. Let's say I take something with a vector input, just like the length node here. Now it has a vector input. Bump and normal are both vector inputs. But you'll notice that in this case, I can plug a scalar into it. Now this may seem odd and confusing, and you think, okay, why can I plug into a vector here but I can't plug into a vector there? It is because sometimes on different nodes or different node inputs, most usually the end node, the destination node of the network, a given input has to receive a certain type of data. So here on the surface node, the normal and bump inputs must be receiving the right kind of vector data. That's why you cannot plug in a scalar. But you will see as we go along that connections like this do make sense. And that, of course, is the important part to knowing and understanding what connections you can and cannot plug together, is whether or not they make sense. In a few instances, you will find it's possible to connect two things together that don't really make sense. And when you do that, you get weird results that aren't really useful for much. But most of the time, you'll find that there is a logic which you can apply to know and to plan which connections you are going to plug to which other connections. And to, of course, help you select from all of these different types of node that you've got available to use in your node editor. So then, let's take a look at a couple of these cross connections and how and why they work the way that they do. Let's start most simply of all plugging a scalar into a vector. I've got a node motion on the bone here, so if I just plug the scalar straight into its position, what we'll see is it jumps, and if we look in the corner we can see it's gone to 1, 1, 1 meter on all three axes. Reason why? The scalar is set to 1. Of course, you'll remember that a vector is just essentially a collection of three scalars, and when you plug a scalar into a vector like this, the single scalar just goes to each of the three slots, as of course we can also see easily on our input SPI there. Same of course is true for an integer. That's no different. In this sense it's treated much like a scalar. If we pop back to Surface Editor for a moment, then we'll see what happens when we connect a colour, which is also of course a triplet value like a vector, is that in the case of 1 we get white. Reason why, if we plug it into the colour here on our SPI, we can see that we get 255, 255, 255. When colours are fed or interpreted from scalars, they're fed essentially as multipliers. So red 1 is basically read at 100% or maximum value, or as we're used to calling it, 255. Colour outputs still deliver 0 to 255 values. But when they're plugged into scalars, then of course they become converted the other way. In this case I've got a grey here, 200, 200, 200. Were it a full 255, then I would have 1. What this brings us on to, before we go too much further, are two very important notes about the node editor. First is a note on, again, the dreaded topic of the math in it. What you will find in node editor is that an awful lot of the math is basically just adding up or subtracting zeros and ones. So many values that you will use from textures, normalized vectors, and the like come as 0 to 1 values. As such, you'll find that pretty much everything either has or can be remapped into a 0 to 1 state and treated in that way. And to that extent, all you need to do to make sure your networks are built correctly is tot up the ones and zeros as you go. It's pretty straightforward. If you can count to 1, you can do probably about 80% of the actual, arithmetic that you need to when using the node editor. This simple fact of taking your 0 to 1s and adding them up, multiplying them, and so on through your chains of nodes also brings us to the next point, which is follow the numbers. It's easy enough to just go connecting things up here, there, and everywhere, but people run into problems with things and they're not sure why. Follow through on the numbers from one node to the next, to the next, to the next, and see how the number is being transformed. Okay, so that's turning into a 1 here, and then the next node turns it into a 2, but this other one divides it by 4, and just tick them along. That's how you'll find the causes or sources of any problems. This treating colour channels as 0 to 1 as well, 0 to 1 on red, green and blue, is of course what allows colours and vectors to interact in the way that they do. Because of course a vector of x, y, z, 1, 1, 1, can simply have effectively the axis names changed and become R1, G1, B1. And so when you plug a 1, 1, 1 vector into colour, you get 255. Plug in a 0.5 vector and you get 50% grey. Start plugging in mixed or different values and you get a different colour mix. And that of course allows you to do funny little tricks like taking a null and connecting its position to something's colour. And then as the null moves, you get this little interactive colour slider control. It also of course means that you can use the colour tools like mixers and gradients to blend vectors, because you're just blending their scalar values, but 3 channels of them. The other cross connection to be aware of comes back to integers. We saw of course you can obviously plug those to colour, scalar, whatever other values. It's what happens when you plug to them. I don't have any integer inputs on the surface here, but I've got one that pipes through. So you can see that whatever value gets entered here, just pops up in my SPI there. But of course, what if I was coming from a scalar or similar? Well, basically, scalars are always rounded down. So 1.1 is 1, 1.9 is 1. 2 then eventually becomes 2, but 2.99999 is still 2. Then we also have the question of what happens when you connect a vector or a colour to a scalar input. What simply happens when you do this is that the first entry, or the first channel, is used as the scalar, and the others are just ignored. It makes no difference what is entered into them. Colours, however, are slightly different, because they are treated as a whole colour. And so whilst white, 255, 255, 255 equals 1, 2550 does not. So it's not simply the first slot that is being taken. It's the combination of all 3 slots divided by 3. So since 255 represents 1, it's essentially 1 plus 1 plus 1 over 3. So that there pretty much is the story of cross-connection between our types and how you can feed numbers around your network. There's just a couple of last things that we need to look at here. First of all is something to do with vectors. More specifically, it's to do with angles. You notice that I've got, as well as a constant vector direction, and also a constant angle. Now we'll talk more about directions and vectors in the vectors video, but notice that both of these have their inputs in degrees, which is, pretty much what we're used to with angles, right? So if I enter a value for, say, 60 degrees there, and I plug it in, I get 1.04. If I plug it into colour, I'm getting 267, so that's 1.04 times 255. So that's definitely what it is. The question is why? Okay, we are used to dealing in Lightwave with angles in degrees. When we have rotation on an object, it's done in degrees. It's degrees in our graph editor and so on. In node editor, angles are given in radians. These nodes that are made to take an angle let you input that angle in degrees. Well, in fact, you have to input that angle in degrees. If I tried to input the radians value, it would come out as 1.04 degrees. So you will be using degrees whenever the input denotes degrees. But your outputs will always be radians. And if you are grabbing rotation information from something in a scene, its values will always be given in radians also. Now, I appreciate some of you may not like this, some of you may not know what radians are, so let's talk about them very quickly. Basically, all it is a different way of marking out the angles in a circle, effectively. We're already used to a good few ways of doing this, such as the degrees that goes, around from 0 to 360. We're used to that, with of course 90 and 180 and so on. But there's other ways we're used to. We're used to the way we mark it out on a clock. That's just another way. You could draw an angle here and say, what angle is that? It's 1 o'clock. And that is all that the radian is. It's just another unit of measurement for an angular distance around a circle. The reason we have it at all, and the reason we have it in Lightwave, is because of how it relates to the geometry of the circle itself. If you're going to use a method like, 12 o'clock through 12 o'clock or 0 through 360 and so on and so forth, you constantly have to, add up and multiply and divide by certain numbers to work angles into other measurements or things elsewhere. It's been much easier to have a unit of measurement that is directly related to the circle itself. So the radian is basically just taking the radius of a circle, as a length, as a line, however many inches or meters that might happen to be, and wrapping it over the surface, the circumference bit. Okay? So as you get an equal length marked out, that is 1 radian. The reason it's useful and the reason it's linked to the geometry of the circle is because if we recall, the circumference of a circle is equal to 2 times pi times the radius. The radius is the important bit. That means if I take a piece of string, the length of the radius for any circle, any size, and I lay this bit of string, or multiples of this bit of string, around the circumference, I'll get 2 pi bits of string. So 2 times 3.14 pieces of string, 6.28 pieces of string, will always wrap a full circle. That's why it's useful to have. So when it comes to enumerating, you've got, of course, the 1 radian and the 2 radians, and, they seem to be offset from a normal angle. 90 degrees, as we see here, is 1.57. It seems like a bit of an ugly number to have for what is a nice, clean 1/4 division of a circle. This slice is tidy. This decimal place number really is not. The reason it's preferred, though, and the reason it's more useful, if you really mark out the nice tidy slices, then what you find is that 90 degrees is 1/2 of pi, 180 is pi, and of course the full circle is 2 pi radians in distance, or of course angle. So that's why we have radians in the node editor, because it saves you having to use multiply divide nodes here, there and everywhere to try and work with angles and other numbers elsewhere in the system. When you're getting vector coordinates for things and so on, you're getting distances between things, a pivot point to a contact point. This can be a radius. It's much easier to link other things that have to counter-rotate via radians. And as I said before about following the numbers, it does make doing that easier. It really does once you get used to it. As I said, most of the time you don't have to do numbers in your head, so it's not like you're going to have to be figuring out radians. And as we can see, anything where we input an angle automatically outputs the radian value for us, as do rotational vector outputs. So when we're hooking these up, the node editor will just do the calculations in radians for us, and we don't need to worry about it. You can be thinking in degrees if you want. That is fine. The only point where it does become important is if you are using scalar entry fields, such as a scalar node, regular vector node, integer, color, whatever. These values would be expected to be a radian. If I want to have a scalar saying 90 degrees, it needs to say 1.57. Of course, you may wind up with situations where you've got values coming out and you do specifically want to swap them back and forth to get a degree value or a radian value, whatever. Or you're getting a scalar that you want to plug into a rotation that needs to be a radian. That can be frustrating, but it's easy enough to convert. Going radians to degrees, x number of radians times 180 over pi is equal to the same number of degrees. And degrees is just the opposite way round, pi over 180 multiplied by pi over 180. So basically it's just 2 extra nodes in between values to do the conversion. So there we go, the treatment of angles within the node editor and the numbers associated with them. We're almost done, so just one last little thing that I want to take a peek at here is the concept of the set. Most of what we've seen here so far, of course, is just pushing around single values for things. Okay? Pretty much all of the node connections can output and receive sets of numbers. So for instance here I have a gradient node, right? And its input by standard is just x coordinate. This is just a single number, the x coordinate of, well, we're in a surface editor, so in this case the ball surface there. At 0 meters it would be 1 key, at 1 meter or whatever I put into the n here, it would be another key and keys in between. Okay? X coordinate is just a singular value on this singular object. However, if you look at something like the instance info node, you've got ID index. You've also got, of course, position, rotation. These are sets. When you've got instances in your scene, this ID index carries the ID of every single instance. So if I plug this into the input on my gradient, my input is now receiving a set, and it is now that set value that I am mapping. So in this case, my gradient of 0 through 3, any keys on it would be affecting instances numbers 0, 1, 2, and 3. Any instances whose ID was higher than 3 would just be receiving the same as the key that was set at 3. It's important to understand, because this is one of the most misunderstood things about many nodes. For instance, the spot info node that catches a lot of people. When you pull the normal from the spot info node, it's a set of vectors, one for every spot on the surface that is being evaluated. That will change in context. In a displacement editor, we're only displacing the vertices of the object. So object spot, world spot, normal. These are sets that are equivalent to the entire set of vertices. When we're doing surfacing, then it's spots all over each and every polygon. Each polygon is covered with spots, generally the size of 1 pixel in our final render, or whatever render view we happen to be looking in. But whether it is a single number or a set, you can just use them in the node editor in exactly the same way. But you do need to know which is which. Otherwise, when plugging into things like the gradient here, you won't quite see what it is that the numbers are telling you. And that pretty much covers all of the need to know basics for you of the data types, how information flows around the network, how it gets converted, how types connect to types, and the smaller details to make sure that you are connecting the right thing in the right way.